I'd like to spend some time on some of the more unusual trends between the periodic table and the atom. We've had a chance to look at periodic table trends in terms of physical and chemical properties, and then we also had a chance to learn about the atom and about the number of protons, neutrons, electrons, that it has shells, and that the electrons are located in different numbers on those shells. And so I want to connect those two concepts or those two lessons together to build a much broader picture. So the first question or I want to answer is one that we have only very briefly touched upon on the periodic table, and that is, how does the proton-neutron ratio change as you go down the periodic table, and why? So first of all, just a reminder, we have protons that have positive charges, and we know that when two positive protons come close to each other, those two positive charges will cause those protons to propel away from each other. So they will repel away from each other. And thanks to the neutron, that actually doesn't happen. And so we'll use two examples here. You'll notice on the left we have nitrogen. On the periodic table, it tells us that nitrogen has 7 protons. And that means that we can figure out what the number of neutrons are based on the atomic mass, and that is always found on the bottom of the periodic table. In this case, it's 14. And so we know that number of protons plus the number of neutrons plus the number of electrons will be the atomic mass. And just as a reminder, electrons are so small they have no mass. So we can essentially say that the number of protons plus the number of neutrons equals the atomic mass. And we know that each proton and each neutron has 1 atomic mass unit. So if we know that we have 7 protons, that means we have 7 atomic mass units. And we know we need to get to 14. That means that there's a 7 atomic mass units that are missing, that are made thanks to those atomic mass units come from the neutrons. And we know that each of those 7 comes from 1 neutron, so that it must have 7 neutrons, 7 protons, 7 neutrons makes the atomic mass be 14. And you'll notice that nitrogen is a relatively small number. Now, if we move down the periodic table and just in the same group 2 rows down, you're going to find arsenic. Arsenic has 33 protons, but you notice it does not have 33 neutrons, because if it were to have 33 neutrons, the atomic mass would not be 74, but would be 66. And instead, we have far more neutrons than we have protons. And this is because, just as a reminder, remember those positive protons, those 2 positive charges want to repel each other. And these neutrons act as a buffer, as an insulator. And the more protons you have in the nucleus, the more insulation you need, which means that you need more neutrons so that these protons can coexist amongst each other. And you will see that as you go down the periodic table, that the number of protons does not equal the number of neutrons. Instead, you almost always have more neutrons than you have protons, because they act as an insulator. The next question that I want to explore is, what do the pegs on the cards mean in relation to the atom? And let's take a look at some of our Bohr diagrams and then compare it to the actual atoms. So you will notice that, thanks to my pen perhaps, you will notice that, hopefully with my my pointer, that I have here on the left-hand top side lithium. It has 1 valence electron. And remember, the valence electron is the outermost shell, and you ask yourself, how many electrons does the outermost shell have? It has 1, and you'll notice that that means that on our element cards, that was indicated by 1 peg. We have sulfur here, and if you look at the valence electron shell, that remember is the last shell, you have 1, 2, 3, 4, 5, and 6, and you'll notice that those pegs are exactly counting up to 6. So the valence electrons are representative of those pegs. And just as a reminder for patterns, as you go down the periodic table, in the same group, you always had the same number of pegs, which means you always have the same number of valence electrons. As you move across the periodic table, you always had 1 more peg. On the far left, it started with 1 peg, then it moved to 2, 3, 4, all the way to 8. That means that the first elements on the left-hand side will always have 1 valence electron. If you move 1 to the right, those will have 2 valence electrons. Skip the transition metals, and then in that third group, you start having 3 all the way to 8. You cannot have more than 8 valence electrons on the outer shell. So how do the number of shells correspond with the periodic table? Well, you will notice that when you were drawing Bohr diagrams, and here I have a Bohr diagram example of hydrogen. It has just 1 shell. Lithium, you'll notice, has 2 shells. In the first shell, there are 2 electrons. Remember, you can never have more than 2 in the first shell. And in the second shell, we have just 1 left over because remember, lithium only has 3 electrons. For sodium, sodium has 11 electrons. That means it has 2 in the first shell, 8 in the second shell. Remember, you cannot have more than 8 in shells that are larger than the first one, or other than the first one. And so that we're now at 2 plus 8 equals 10. And remember, I said there are 11. There's 1 left in the last shell. Notice that I have 3 shells. And for potassium with its 19 electrons, I have 1, 2, 3, 4 shells. If you now look at your periodic table and look at the far left-hand side, and I have a little screenshot of what that looks like. Do you notice how you have 1 hydrogen, the number 1 next to hydrogen, just like you have 1 shell? Notice how you have by lithium, right next to lithium, you have the number 2. That means that this entire row or period will only have 2 shells. For sodium, you have the number 3. Just like the image shows, you have 3 shells. Same thing, all across the periodic table, that row will always have 3 shells. And then down to 4. And it continues all the way to 8. So why do atoms get larger as you go down the periodic table? And why do atoms get smaller as you go across the periodic table? And with that, I'm going to show you a video that explains